So let's have a quick look at how we write a number in scientific notation. So scientific notation is a way for us to write really big numbers or really small numbers in a more manageable way. And the form that it takes is a times 10 to the power of n, where a is a number that's greater or equal to 1 but less than 10, and where n is a natural number. So the best way to explore it is through a few examples. So let's say we have a really big number, 75 million, and we'd like to write that in scientific notation. So the first thing we got to do is we got to pick a number between 1 and 10. And so we can see that this number 75 million starts with a 7, and 7 is a number between 1 and 10, so 7 is going to be the first digit. We put a decimal place, and then anything that comes after the 7 we want to write after the decimal place. And so we can see that 7.5 is the A term for the scientific notation, and it is indeed a number between 1 and 10. So the next thing is, how do we come up with the power, the n number? So what we do is we write multiplied by 10, and then to the power of the number of digits after the first digit. So 1, 2, 3, 4, 5, 6, 7. And we put down a 7. And so 75 million, if we convert that to scientific notation, is 7.5 times 10 to the power of 7. So let's have another example. Let's do 432 billion. So this time we have 9 zeros. So again, we need to choose a number between 1 and 10. So the first digit in this big number, 432 billion, is 4. So we write down the 4. And then a decimal place. Because we want a number between 1 and 10, there has to be a decimal after the first digit. Now, is there any digits after the 4? Any non-zero digits, that is? So we have a 3 and a 2, so we'll write them down as well. And then multiplied by 10 to the power of, this time we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 4.32 times 10 to the power of 11. So 432 billion can be written in scientific notation as 4.32 times 10 to the 11. Okay, sometimes there'll be lots of non-zero digits after the first digit, and so we may be told to give the answer to 2 decimal places, or what's called two significant figures, something like that. So let's see how we do that. So let's say we have a number 532614900, and so we want to give our answer to 2 significant figures. And what this means is that we have 2 numbers at the front, and then anything after the first 2 digits we don't count as being significant, and so they're zeros. So this number 532614900, we can see that if we were to round that off to 2 significant figures, it would be the number 530000000. So we've just rounded the number off, and we're saying that 532614900 is approximately 530000000. And so 53, they're the 2 significant figures. Now, how do we write this in scientific notation? Well, it's 5.3, so the first digit 5, followed by a decimal point, and then any digits that come afterwards, so the 3, and then times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 this time. Now you might say, you know, why did I round it to 2 significant figures? Should I not have just kept all the digits in it? It's sort of a pointless exercise if we do that. If we say that this is going to be 5.326149, so use all the digits after the 5 that aren't zeros, and then do times 10 to the power of, it'll still be 8, 1, 2, 3, 4, 5, 6, 7, 8. Well, it didn't really make the number much more manageable. It's still a really big number with lots of digits in it, and so we want something more manageable, something that's like a bit more compact and a bit small when we write our scientific notation. And you can see that all the scientific notation numbers that we've written down have been a bit more manageable than the numbers we had at the start. Now, sometimes you'll be asked to write a number in scientific notation that probably doesn't really need to be. There might be a small little number anyway. So let's say we have 7,300, and you can be asked to write that in scientific notation. Now, what will happen is when we convert this and we say that it's 7.3 times 10 to the power of 1, 2, 3, the actual scientific notation answer is just as big or bigger than writing down the actual number itself. So it doesn't really make sense to write scientific notation for hundreds, thousands, even tens of thousands. But then obviously as you get bigger, it makes more sense to use scientific notation. So always have a look in the question just to see like how many significant figures are they interested in. So we'll do one more example, and this time we'll go to 3 significant figures. So right, so we'll pick the number 632,410. So the first thing I would do is if I was rounding this off to 3 significant figures, I'd say, well, that's going to be 632,000. You always look at the number after, let's say, the 3rd significant figure. If this was a 5 or bigger, we'd round this up and we'd say 633,000. So it's kind of similar to working with decimal places. Now, what's this in scientific notation? Well, this is going to be, the first digit is 6, then a decimal, 32, times 10 to the power of 1, 2, 3, 4, 5. And that's our answer. Okay, so that takes care of really big numbers, but what about numbers that are really small? How does it work for really small numbers? So let's have a look at a really small number and see the difference in using scientific notation for those kind of questions. So let's say we have a number 0.0000432, and we want to write this number in scientific notation. So what we do is, again, we go and look for the first digit that's not a 0. So all these zeros at the start, we don't count those when we're looking for our number between 1 and 10, because obviously 0 isn't between 1 and 10. So the first actual digit is the number 4. So if I write down 4 and then my decimal point, why a decimal point? Remember, we always have to have this A as a number between 1 and 10. So 4 is a number between 1 and 10. Now, what comes after the decimal point? Well, any digits that are left in the sum, so 3, 2, and then times 10. Now, we don't want to put a positive power up here, because if we put a positive power up here, well, then this is going to be a really big number, and we can see that this is a really small number. So how do we take care of really small numbers? We count the number of zeros, including the 0 on the left of the decimal point. 1, 2, 3, 4, 5. But it's not 10 to the power of plus 5. It's 10 to the power of minus 5. Okay, so let's have a look at another example. So let's say we have 0.0324771, and this number goes on for ages. And what we want is we want an answer to 2 significant figures. So again, I'm going to write down this number. I'm going to round this number to 2 significant figures. So this is the symbol for approximately. So this number is approximately 0.03, and then I look at the 2. That's my next significant figure. 3 is the first significant figure. 2 is the next one. And is the number 5 or greater, or is it less than 5? So it's less than 5, so we keep a 2. If it was 5 or greater, we'd round that up to a 3. Now, turn this into scientific notation. It's 3.2, so 3 is the first digit. Then we put a decimal, and then the 2 times 10 to the power of... And how do we come up with our power again? First of all, it's going to be a minus power because it's 0 point something. And then we count the number of zeros. 1 on the left and 1 on the right, and so that's 10 to the power of minus 2. Okay, and it's 2 significant figures. We can see them there. Okay, let's give an answer this time to 2 decimal places. So how would that be slightly different? 2 decimal places. So 0.00000057634. So this time what we're going to do is we need to round to 2 decimal places, but we know that the 5 is going to be the first digit. So I actually need 2 more digits after the 5. So if we round this off, we have 0.000000576. Now, I took a look at the number after the 6. Again, it was less than 5, so I kept it as a 6. If this 3 was a 5 or greater, I'd round this 6 up to a 7. Now, turning this into scientific notation, we have 5.76. So the first digit we see, that's non-zero, that's the main number, 5. And then 0.76, any digits that come after it. And again, here we were rounded to 2 decimal places, so we could have had 5.7634, but when they said 2 decimal places, we only went to that far. Now, multiplied by 10, and then how many zeros have I? 1 on the left, and then 2, 3, 4, 5, 6, 7, 8, and it's minus 8. Again, minus because this is a really small number and not a really big number. If they had said 2 significant figures, how would the answer be different? Well, 2 significant figures, we would have the 5, and we only want one other significant figure after that. Now, would it be 7 or would it be 8? Well, how do we know? We look at the number after the 7, so after the second significant figure. It's a 6, which is bigger than 5, and so we round the 7 up to an 8. And so we get 5.8 times 10 to the power of minus 8. This answer is 2 decimal places, and this answer is 2 significant figures. Now, the very last thing we're going to do is, let's take a number that's in scientific notation and turn it back. So let's have a go at turning the number 6.32 times 10 to the 4 back into our standard notation. So here we have scientific notation, we're going to put it back into a number that we're more used to working with. So I'm going to write down the first 3 digits, 6, 3, 2. I'm not worried about decimal places or anything like that. And I know that there's 4 places after the 6. So we have our 6, and then we have 4 places. 1, 2, and then we fill the rest of the places 3 and 4 with zeros. So 6.32 times 10 to the 4 is 63,200. Let's try another one. So let's say I have 8.2 times 10 to the 7. So I write down the 8 and the 2. I know that there's 7 digits after the 8. So one of them is a 2. And then 6 more of them will be zeros. So 1, 2, 3, 4, 5, 6. And it's a good idea to work from the end, and every 3 put in a comma, so it's easier to read that number. So that number is 82 million. Okay, we'll try one more. So let's say we have a number 5.132 times 10 to the 8. I write down the 5, the 1, the 3, and the 2. I know there's 8 digits after the 5. I have 3 of them written, and so I need 5 more zeros. 1, 2, 3, 4, 5. And then put a comma every 3 spaces, and that's the number 513,200,000. Okay, so what about the really small numbers then? What about 2.12 times 10 to the minus 5? Well, this time I'm going to start with the 5, and I'm going to write down 5 zeros. 1, 2, 3, 4, 5, and then I'm going to put a decimal point after the first one, and then I just fill in the digits that are left. 2, 1, 2. Okay, let's try another one. So what about 4.7 times 10 to the minus 3? So I start with the 3. There's 3 zeros. 1, 2, 3. I put a decimal point after the first one, and then I write down what's left. 4, 7. Okay, one more. So let's say we have 6.147 times 10 to the minus 8. So again, I'm going to start with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. A decimal point after the first 0. And then what comes at the very end? Well, all the digits that I have here. 6, 1, 4, and 7. Okay, so now we know how to convert numbers into scientific notation and also to turn them back. Both really big numbers that have positive powers and then really small numbers that have negative powers.